In this video, we're going to look at how to write radioactive decay reactions. In radioactive decay, radioactive nucleus spontaneously breaks down by emitting radiation. We can write this out through a nuclear equation. We are going to look at two types of radioactive decay in this, but a nuclear equation is where you have a radioactive nucleus and it decays, spontaneously breaks down, produces a new nucleus and radiation. The two types that we're going to look at in this video are alpha radiation and beta radiation. You can also have positron emitters and gamma emitters, but we're just not going to look at those particular reactions in writing these. One thing to keep in mind when you're writing your nuclear equation is that the sum of the mass numbers and the sum of the atomic numbers on one side of the arrow have to be equal to the sum of the mass numbers and the sum of the atomic numbers on the other side of the equation. So it has to be balanced in that respect. So let's look at an alpha decay reaction first. An alpha decay reaction is going to emit an alpha particle. So an alpha particle is written by the Greek letter alpha. That's how it gets its name. So it is an alpha particle. It is essentially a helium nucleus. So it has two protons, which is indicated by the 2 on the bottom, and it has a mass of 4, which tells us that it has 2 protons and 2 neutrons. And so the mass number is 4. The number of protons, the atomic number is 2 here. So it's the helium nucleus. Let's look at an example. We're going to take, let's see, 251 nobelium, and this is an alpha emitter. So when it undergoes alpha decay, it gives off an alpha particle. So that is one of our products here. And the other thing, you can come up with what it is because the mass numbers have to be equal on both sides and the atomic numbers have to be equal on both sides. You can figure out what nobelium becomes after it undergoes an alpha decay process. And so we can look at our mass number on the top, and we have 251, and we're going to subtract 4 from that because that's what our alpha particle has. And so in doing the math from that, you end up with 247. So that is the new mass number over here. And then for the atomic number on the bottom, you have 102 minus 2, which gives us an even 100. So looking at the periodic table, you can look up what element has an atomic number of 100, and you will find that the symbol is Fm for fermium. So this would be the complete alpha decay reaction for nobelium 251. Okay, so let's look at a beta decay reaction. So in a beta decay reaction, it's going to emit a beta particle that is written by either the Greek letter beta or by this symbol here, 0 over -1 with an electron. So it emits a beta particle. It has no mass, and we have a -1 for our atomic number down here. And the beta particle, so it's essentially an electron, and you might think, okay, but this is coming from the nucleus. How do we get an electron out of the nucleus because we only have protons and neutrons there? Well, the beta particle comes as a result of a neutron breaking down into a proton and an electron, and that electron, being the beta particle, gets emitted from the nucleus. So we have in a beta decay a neutron becoming a proton. So let's see what that looks like as a reaction. We're going to look at 188 over 80. This is radioactive mercury, and this undergoes a beta decay, so it gives off a beta particle here. And so to find out what the other particle is, we have 188 subtracting 0. So that gives us 188 for our mass number. So when it undergoes a beta decay, your mass number doesn't change. But down here for the atomic number, now we have 80 minus a -1. So remember, when we're subtracting negative numbers, we're adding it. So that becomes 81. So that's our atomic number. Again, go to your periodic table. And this is thallium. And so that is an example of a nuclear reaction for a beta decay. So these are fairly straightforward to write. You just have to remember that what the particles are, what their symbols are, and then to balance the mass numbers and atomic numbers on each side of the arrow.